Hi, so Ben introduced. My name's Ian Stokes. I'm a network engineer with Intel. I suppose previous to date, I've worked on QoS and kind of ingress policing in the OVS project. And today I just want to talk about IPSEC and OVS DPDK. So just something I've been playing around with for the past year, kind of more of a learning exercise to kind of see what the pitfalls will be and just kind of present what I've found to date to the folks here. So just a quick overview of the content that we're actually going to go through today. So I suppose the use case overview, why do we think this was needed in the first place? Proposed IPSEC functionality. IPSEC is fairly large, so what aspects of it do we need to actually provide for our use case? Then, as usual, we'll look at kind of the RFC that I'd done and how that worked, but coming out of that, the design considerations really. The RFC will have to change before its final upstream, but I can show some of the problems I kind of hit already. And then finally, some performance metrics and future work. So let's kick off. I suppose today, if we had a fairly simple data center, something like this, 2 servers and an IP network, we want to throw some VMs on either side. We can see the VMs actually correspond to each other, they're color-coded. And we would expect something like our traffic in an ideal world to kind of, I suppose, come along like this. So it's playing nicely, VM1.1 is going to VM2.1, and that's great. But talking to customers, they kind of said if their VMs are being provisioned in a data center, there's kind of a question they ask themselves really, which is, do they trust the network that's being provisioned on? And if you don't, what are the kind of problems you can hit? So I suppose one of the first things is, let's say we start scaling the number of VMs out. It's fine when there's 4, but if you start scaling them out, things could happen like the IP start overlapping, your MAC address could start overlapping. You could quickly get yourself into something like this, which you really don't want, where you have VMs sending traffic to each other that they shouldn't be doing. But you have another problem as well. If the traffic is being sent like that in the IP network, not only could they go to the wrong people, but what about the IP network itself? If the traffic's being sent in the clear, what does that mean? Could it be modified? Are you sure who's being sent by? So we kind of sat back and we kind of asked the 4 questions. Well, here we have a couple of problems. Our traffic isn't isolated. It could end up at the wrong VM. It's not confidential. Anybody sitting in the IP network could kind of see what's being sent in the clear. Its integrity isn't protected. How do we know it's not being modified in transit when it's being sent and received? And then finally, it's not authenticated. How do you know that it's come from the person you think has sent it? So if you were to take OVS today and take a quick stab at maybe fixing this with what we have to hand, I suppose in OVS DPDK at least, you could do something like VXLAN, and it would look like this at a very high level. So we'd introduce kind of VTEP termination points on either side. We would set up our tunnels, and there'd be a nice VNI for each VM. And that way, if this is set up correctly, you can be reasonably sure that, hey, traffic being sent from the VM on the left has a VNI. It'll go over VXLAN tunnel 12, and it should arrive on the right to VM2.1 at VNI 12. And so you've kind of isolated your traffic nicely here. But let's go back to our questions again. So you've isolated it, great. Still not confidential. Anybody in the network could plug in and see that, okay, you've just put a VXLAN on this, great, but I can still see it. Its integrity is not protected, you can still modify it. And again, it's not authenticated. You still couldn't be sure when you're receiving it. Sure, it's isolated, but who sent it? So we kind of played around the idea, what if we were to kind of bring in IPSEC as just kind of some skunk work and kind of, what could we do? So it would look like something like this. You still have your VTEPs, but now we brought in IPSEC termination points on either server. And the idea here is that IPSEC should be able to give you, should be able to provide the isolation. We're using the VXLAN anyway. It should be able to provide the confidentiality. So IPSEC can do, cipher and encryption. It should be able to do your integrity using your hash digest. And finally, it'll be authenticated. The concept of security associations in IPSEC is that essentially it's keys being shared between 2 people and they're not being shared with anybody else. So there's a degree of security there that unless those keys have been compromised, you can say that pretty much you're ticking the box on authentication. So IPSEC's a fairly big RFC and there's a lot of different aspects. So we kind of said, what could we cherry pick out of it to enable this? Because we don't need all of it straight away, especially just for early RFC work. So I suppose, given a standard packet that looks like this, what do we need for CIA, confidentiality, integrity, and authenticity? And I suppose the first thing I looked at was, right, there's 2 different protocols available in IPSEC. There's ESP mode and there's authentication. Authentication will give you just that, authentication, but the packet will still be sent in the clear. So we need to go for ESP. What ESP allows you to do is essentially, encrypt the packet as well as authenticate it, which is really what we want to hit for this use case. There's two different modes that can be sent in. So for anybody not familiar, there's transport and tunnel. Tunnel, IPSEC would add its own header, essentially, or Ethernet header and IP header. But in tunnel mode, you just kind of slip in behind the existing Ethernet IP header. This is the idea we kind of thought, well, if we have VXLAN, then we'll have an encapsulated packet with an Ethernet header and an IP header already. So let's just slip into that for the moment. It's kind of a simpler use case. And then we'll have to put our ESP padding at the end of the payload also. So in terms of like type of cipher and encryption that you need, going by the RFC, I think we have to support AES-CVC and also AES-GCM. That's just for the encryption. So that would encrypt from your L4 header just down to your ESP trailer. And then in terms of actual authentication, we kind of said, look, it's HMAC SHA-196 is the must-have. Now I should call out here that AES-GCM on the left-hand side is a combined cipher, so it does ciphering and authentication in one go. So really, you could put that in both columns, but in terms of just, for simplicity, we've kept it in the encrypted side, but it is a combined mode. But if you had this should be enough to kind of, hit those resolutions that we said, hey, look, integrity, confidentiality, and authentication. So with this in mind, we kind of came across in the RFC, we said, so if this is what we have today for VXLAN, so we have a virtual machine, it's hooked into our bridge with a VXLAN port, 2 different bridges and a DPDK port facing out onto network, it would be cool to kind of keep it as simple as possible, and it would just look like this. We just swap out the VXLAN port and bring in a VXLAN IPSEC port as part of the RFC. And what does that actually look like, and what's this functionality? Well, VXLAN IPSEC port, it still handles VXLAN encap and decap, so IPSEC works at the IP layer, so we still need to guarantee that we have the IP header. So let's just encap it with VXLAN anyway, as usual. But it'll also handle the encap and decap of ESP. More to that, we have an associated DPDK crypto dev. So if anybody's not familiar, in DPDK, this is a crypto dev API library. It kind of handles things like cipher encryption, decryption, digest generation, verification. And just a note on that, because the crypto dev library, it's kind of designed to work with both hardware and software. So it's just kind of a generic wrapper to work with both of them. So in this case, we were kind of looking at testing with the Intel Quick Assist QAT devices and then a VDEV crypto PMD. And in the RFC, I kind of concentrated on the software solution first because it was a bit more flexible. So just a quick kind of run through of what we're going to look at next. We're going to look at the encap and the decap. I suppose if you just go to the actual way this works, we've all seen this before. We're going to send a packet from VM1 out of the hypervisor 1 and into VM2. And we'll just look at stage by stage how that actually happens in the RFC we've done. So we have a packet in VM1, and he's being sent out on his way to VM2. So when he arrives at our vHost user port, this is what he's going to look like. Standard packet, Ethernet header, his IP, his L4 header, and his payload. From there, he'd be routed into our VXLAN IPSEC. So we kind of took advantage of the existing VXLAN kind of the VXLAN code base and kind of expanded it just to do IPSEC. So we had this routing pretty much set up based on destination and MAC for the VTEPs. We've just modified it to use VXLAN with IPSEC also. And when it arrives, we have to do kind of 2 operations. First, we need to actually encap for the VXLAN ETH IP. So you can see we're adding an outer Ethernet header, an outer IP. We then add our ESP header and our initialization vector. So that's kind of cipher dependent really on IPSEC, but these are the kind of packets you have to add at this stage. And then just after that, we put in our UDP and VXLAN headers. So it's VXLAN over IPSEC in this case. So we're slotting in just after the outer IP header, but before the UDP header. So that takes care of the header side of it, but for ESP, you have to take care of a trailer as well. And so just after original packet, we need to add cipher padding, and that's cipher dependent. They have different requirements for that. An ESP trailer, which will tell you kind of how much is in your cipher padding and what's the next protocol you're going to point to. In this case, would be a UDP header. And then your ESP digest. So this comes back to our authentication. So just a hash digest of pretty much from the ESP header to the ESP trailer. So our packet then would just get routed out, as per usual, out into the network. On the decap side, I suppose, if our packet arrived, we had to do a bit of work here, because although the packet arrives at DPDK1, what's it look like? Well, at this stage, we have our outer and Ethernet IP headers, you have our ESP header, but the payload's encrypted. And OVS at this stage didn't have an idea how do you route this, so we kind of had to actually modify the OF proto layer on native tunnel terminations to take into account the ESP header. So that was kind of something we had to add into kind of the EMC extraction and the flow structures themselves. That hey, look, there's an ESP header now with a value, and this then gets used at the classification point for a native tunnel. And using that, we're just able to route straight into our VXLAN tunnel if you were to break this encrypted payload out, what it would look like would be from your initialization vector down to your ESP trailer. That's what's being encrypted. So you can't access this, which would mean you don't have access to your UDP or your VXLAN header at the moment. So that's why we need to do this extension just to enable routing into the VXLAN IPsec tunnel itself. So once we get to the VXLAN tunnel for decap, I suppose there's kind of two operations, and just to call it out, we use our crypto dev that's associated with the VXLAN IPsec port itself to first validate the digest. So make sure that nobody's tampered with this in the network. If they have, we'll drop it. But if they haven't, great, let's decrypt it. And at this stage now, we have access to the underlying UDP and VXLAN. So now we can do our metadata extraction for the tunnel. And then finally, we'd pop the headers. So essentially pop all your VXLAN ESP headers and trailers and send the packet in for recirculation, at which point the vSwitch will just send it on to VM2. And so that's kind of what we did with the RFC V2 that we did this summer. Coming out of that, that wasn't the final design. It was more just a learning exercise, as I said, but there was actually some design considerations that became quite apparent that we really need kind of input from the community on. And I suppose I'm going to break it into like Intel QAT devices and VDEV Crypto PMD, because although they subscribe to the CryptoDev API, there is differences to what's going on under the hood, and it can influence your application, how you're designing it very differently. So I suppose in CryptoDev creation, a QAT device, when it's attached to CryptoDev, it's not a physical function, even though it's a PCI card in this case we were testing with. It's actual virtual functions that are hanging off the physical function, and that it's up to the user to kind of create these prior to like launching Open vSwitch. So it's just, that's kind of something, it's not done dynamically at runtime. But with the VDEV Crypto PMD, that was something we can just create on the fly. So essentially, we just called the VDEV initialization API for a crypto VDEV. So that's kind of a difference between the two. It's kind of needs to be called out to end users, really. ArcsQ pair capabilities. So this is the pair capabilities for doing crypto operations on a CryptoDev device. For QAT devices, you have 2 Q pairs max per VF. And then on a VDEV Crypto PMD, you have 8 Q pairs by default max. You might say, okay, well, what's the difference there? But if you're looking at something like a lockless design where you don't want contention between cores for the same queue, you might decide to start, well, let's do a queue per core, essentially. That could be one aspect to look at. But as you can see here, if you've only 2 queues per VF, you might have to do some math to say, well, if I'm going to support 8 CPUs, then I'm going to need, 4 VFs? Or do you just do a fallback where, you use your VFs first and then you create VDEVs on the fly to take over for queues that cores need to correspond to? I suppose then the DPK PMD requirements themselves. So obviously for the QAT side, you need a QAT card and you need to enable the libRT PMD QAT and DPDK. However, on the VDEV side, to take advantage of this, we had to actually use an external library it's open source by Intel, but it's called the Intel Multi-Buffer Crypto IPSEC for IPSEC. I guess wanted to call this out because this isn't part of any repos. Now, although it is open source, it brings up a problem really if you're a distro, like we can't enable this option as default because it's not going to be part of their repositories. So again, this is a design consideration that I'm looking for feedback from the community. Is this something that's acceptable? Is it okay to go off and use this library or not? And if it isn't, then how do we get around that? And then obviously you'll enable your PMDs themselves. So we use ASNI MB multi-buffer and ASNI GCM to actually enable our 2 crypto PMDs for software. I suppose just continuing, an obvious one, but again, people keep overlooking this. It's an asynchronous operation. What does that mean? So for hardware and software, it's going to be asynchronous. So if I have 6 crypto operations that I want to actually enqueue to my CryptoDev device, fine, call the RT crypto enqueue burst. That's great. But if you think that you can just call what I want to decrypt 6 and it's going to wait, no, it'll dequeue as much as it can, but it might just give you back 3. So you're going to have to either have a flush mechanism or else keep a tab on how many crypto ops you've enqueued versus dequeued, and remember to go back and get that. So that's kind of, although simple, it does have an impact on the design. It's something worth calling out. Another kind of simple trivial one, but it's something that we're kind of thinking how to do this, security association establishment. So I mentioned earlier there's a security association in IPSEC. It's kind of the glue that's holding things together. So between 2 kind of IPSEC people using IPSEC, what we would say they have a security association each. This security association would say, hey, what are your crypto transforms? What cipher algorithm are you using? What authentication algorithm are you using? What's your cipher key? What's your authentication key? This is kind of really key, this is important information, and it's how do you keep that secure? Where should it actually be stored? Is it okay to put it in the OVS DB? Or is it just something that you put back to a user and say, look, you put it in a file somewhere, you handle security permissions, we'll read it, but really we're going to push back on you. Yep, just some performance metrics from the earlier work we'd done. So this is a really simple use case. It's so just encapsulation packets that are coming in. We were using one PMD and we were using a software VDEV. We were doing 2 crypto operations here. So we were doing one operation to do the ciphering, so using ASCVC. And then we had to do a second operation then for HMAC SHA-196. So this was really just kind of stress out the system really with one PMD. I wanted to see what I could get out of it. And in the blue, we have the TX rates. We're trying to get line rate in. And then in the red is just the NCAP rates we're getting out. So I suppose what I want to call out here is with 64 bytes, you could almost argue it's not even a realistic use case. I mean, your encapsulation becomes so large that you're becoming larger than the data you're actually trying to send. So, but just for completeness, we've included it. But as you can see, the real use case kind of starts coming around between 256 to 512, and that's where you start seeing the gains. Again, this was just using VDEV. We could move to using QAT. Recently, I started to do that, and we're starting to see about double the performance numbers, but I wasn't comfortable completely putting those stats out there yet because I need to just make sure that they're genuine numbers. But again, you could also probably change up in the sense that this is 2 crypto operations. If you went to something like GCM, I said that was a combined cipher. So in one pass, that can do both a cipher and an authentication. So again, you'd be halving the amount of crypto operations. So that's kind of a way you could actually speed this up a bit more again. And I suppose just kind of future work really from that point of view. So obviously, we need to add GCM combined mode support. I think that's a no-brainer. I'm working on that currently. I think we need to add IPSEC tunnel support. This was great using transport, but it's kind of just, you're kind of jimmying the VXLAN method for the moment. I think down the road, after doing this, kind of figured out how we could add a tunnel, and it's actually not that troublesome really to do. But I think it would be the next step really to go, where just the IPSEC tunnel itself adds its own header and encapsulates everything underneath. IKv2 support, this is an important one way further down the line. But for the moment, what I'm suggesting is that right now, people should just set these keys up manually. And that's fine for a test bed. But if you want to use this in industry, how's that going to scale? How is rekeying going to be handled? It's something you really got to start thinking about now, because there's no point in forgetting about it. It's a problem that's not going to go away. Potentially on that one, my thoughts are, I think StrongSwan has a Userspace plugin. I'm wondering maybe there's something we can do there to maybe tie into that. But that depends then on the community's opinion on using a third-party feature. Would the community prefer to see something like OVS try to implement its own IKv2? Or is it okay just to plug into something that's already doing that job well? I know which one I vote for, but it's worth flagging it. I suppose the architecture changes. Just on the packet batching, I suppose those, full disclosure, the performance figures I saw there, when I originally did this, the tunnel NCAP and DCAP were single packet NCAP and DCAP. So that's really going to kill your performance. So I'd actually modify that to start taking into batches, essentially, just out of, just to get those figures. And saw performance boost kind of across the board. There's a bit more duplication in code, but it was just something that if you want to do your NQ and DQ at that level, maybe we don't. That will kind of be a performance change, or that would be an architectural change we might have to start considering. Is it better to do batches for the tunnel or not? I suppose then a big one, if anybody's here for the DPDK summit for the last 2 days, I don't know how many different presentations were mentioning this, but RT security, things like hardware acceleration for inline crypto, RT security for look-aside crypto, that's a big topic, and there's a lot of flux going on in the DPDK community at the moment. It could be the perfect timing that this is an RFC now, so we can take stock and maybe redesign. I guess my fear here is that let's not implement something for IPSEC and this time next year be tearing it down because something better has come along or it's easier. I think we need to maybe just look at, in particular, just how it's going to tie into RT security. If you're doing partial offloads, I think that'll be okay. You still have to modify a packet manually in software to at least have the headers present. But I'm more thinking about when we start doing full protocol offloads, what's that going to look like? And is that where there's going to be a lot of problems to come? Yeah, so I suppose that's kind of everything here. I suppose thanks for your attention. And if you have any questions, feel free to ask.
And we do have time for questions. So I see one here and one here.
Thank you so much. It's really fascinating talk. My question is, I have 2 questions. First one is, you use VXLAN as a tunneling mechanism. Is that easy to replace something else?
Is it just using, is it why did I use VXLAN essentially to use a transport mode? Is that kind of where you're going? Being honest, it was a really quick way to get something out the door and kind of hit these design problems. I don't see that being the final use case. I think I went as far as in the RFCs, I put a disclaimer at the top that I do not expect these to ever be upstreamed, but that was more to highlight the problems that I was coming across and let somebody kick the tires and try it out. I think there's a lot of different aspects here, and it was just a quick way to get something up onto the community, because it's easy. Like, I'd sent an RFC design previous where it outlined a very high-level interface design. That's fine, but it's not code. So this was just a very quick way. You'd have your termination points. You know, it was also a lesson for myself when I figured out how VXLAN was working, how to actually do IPsec tunneling, and it'll be kind of following the same model. So personally, I'd almost see it being an IPsec tunnel itself down the line with the option then of transport or tunnel mode. Again, it was a good way to do transport mode as well, just to figure it out in the first go. So it's purely from that kind of an exercise, really.
Thank you. And second question is, I see DPDK and even hardware float in the future work. If I want to try it without having all those non-DPDK environment, is that easy to try that out, or?
Sorry, so try it without?
Without having DPDK, no.
Or just do it without DPDK? I don't know, I suppose I'm part of the OVS DPDK community, so I hadn't made that move quite yet. Again, it was just something that I think IPsec was supported, and it still is supported for OVS, but it's done via the kernel, I guess, right? You can still configure that there, and it'll be handled. Us in DPDK, we don't have that luxury, unfortunately. So this is one of these things, it's a duplication of effort in one sense, but that's why we're kind of reintroducing it this way.
Thank you so much.
Yeah, just a quick question. You made the decision to put the VXLAN inside the IPsec transport mode. Yep. Is there a reason, was there any design consideration about maybe doing it the other way around?
Yeah, because you could have done it the other way around, right? You could have done, I suppose one of the things was, we kind of thought, like, is there ever a point where your packet wouldn't have an IP or an Ethernet header? So it's purely just, well, if we do it VXLAN over IPsec, we will just match on the VXLAN's IP termination point, and at that point, we should be okay. I think if we went the other way, you're going to tunnel mode, which is that the IPsec would have to create its own ETH and IP. I suppose there's kind of a performance aspect there. Like, I mean, if the termination point is the same for both VXLAN and IPsec, I was kind of wondering, are you going to literally, the packet arrives, you're going to decap it, and then it's going to be recirculated and come back in, and that's the recirculation. We were kind of wondering, well, look, let's try it without it first from a performance point of view. Maybe you don't need that recirculation. Can you just take advantage of here? But it's a fair point, and it's something I think if people do have opinions of that, and I do expect it to change.
Yeah, I was just thinking that maybe
and I think it kind of breaks, it does kind of break, but I said this was kind of skunkworks as well, and it was just get something out.
Yeah, I just think it would be interesting to try it the other way, just so because you may use VXLANs on a per tenant basis, for instance, and they might want their own credentials, and
I think,
and you might want to route to a different set of servers, that sort of thing.
You may want to. I guess just with the IP, it's just the overhead as well that comes with the IPsec tunnel. But now that I've done it, as I said, it was more just this is quick and easy.
Cool, thank you.
Let's go back. I do expect that to change, definitely.
Sure, thanks.
Just a follow-up question about VXLAN and IPsec. Have you considered how you're going to implement that in terms of a virtual device, like one device that does both VXLAN and IPsec? If you would like to extend that to additional protocols, you would have one device that does, say, GRE and IPsec and GRE, et cetera, et cetera.
Mm-hmm. Yeah, I think that was kind of called out, like when we originally did the RFC, we were saying we'd see how it would go for VXLAN, but yeah, you might extend it to different protocols then as things come along. I do see that being the use case, to be honest.
You mentioned good chunks about crypto. What kind of challenges did you have in terms of key management, especially with related to IPsec and everything?
Sorry, can you just speak up?
I was actually asking about challenges that you had with key management with IPsec when you had a lot more IPsec tunnels and that kind of stuff. Would a key store with OVS would have helped you if such a thing were to exist?
Yeah, I think anything like that would definitely help. At the moment, as I said, I didn't think it was the place for OVS to be implementing something like that. So it was more like what's third party. But again, that's why I'm interested if people have feedback, if they're working anything like that. I'd definitely be interested to know. It'd be really useful. Okay, perfect. I think we're out of time here, so I guess Ben. Or is there any more questions? Oh, okay. Yeah.
I
Sorry,
just had
the red light.
one additional comment. So we actually used to support IPSEC for the kernel version in OVS.
Okay.
So you might want to, we removed that in the 2.7 release, I
I
believe.
saw that, yeah.
Yeah, but you may want to look, like we used Raccoon and then later Strong Swan. So I definitely, for Ike support, we would want to use an external library for that, and there's some precedent for that.
A really good point, yeah. As I said, I think on those we were kind of looking at just how to interface with them from the user space aspect, but I hadn't dived in there. So if that's being used and it's kind of solved, great, I can look
Yeah, I
at
mean, I mean, all that got ripped out, and I think there's a conversation that could be had with, what went wrong with the previous IPsec implementation. I think that had to do with some kind of hacky ways. It had to use SKB mark in order to indicate that it should be encrypted. Yeah. You don't have that problem in DPDK, but anyway, there are a couple people we could introduce you to that were involved in that work that could probably figure out how to do it cleanly for a future implementation.
Sure, thank you.
I'm pretty sure that what we ripped out was a particular method of configuring it, and all the lower level mechanisms are still there. All right, let's thank our speaker.
Okay,